Before we dive into the tutorial notebooks themselves on Julia Box, I have a few slides to take us through to sort of introduce the language Julia and talk a bit about why we might be interested in learning the new language Julia. So first off, my name is Jane Herriman. I work for Julia Computing, and I'm also a graduate student in materials physics. And I'm very much a user of the language Julia rather than a developer, whereas Sacha here, Sacha Verweij, is with us from both Stanford University and the Julia Project. He's one of the core developers of the language itself, and so he's here to help answer questions and hopefully address any interest you might have in going sort of deeper into the development or design philosophy of the language. So I came to the language just a couple years ago as a Python user, and I still use Python for some of my research. It was actually in graduate school that I started teaching myself to program for the first time, so I'm only a handful of years out from writing my first for loop and all of that. And I'll talk a little bit about how I got into Julia from Python while introducing the language. But I first wanted to get a sense of who's here today. So are all of you primarily Python users? Is there anybody that, I guess, has another language that's their primary development language? What languages are you using? Okay, C and MATLAB and MATLAB as well. Okay, and what, I guess, industries or fields are you coming from? Are many of you engineers? Okay, how about in the physical sciences? All right, life sciences? Okay, cool. Economics? Math? All right. What about fields I haven't mentioned yet? What are you in? Geography. Geography. Okay, great. Marketing? And then I saw other. Logistics. Okay. Cool. And how many have tried Julia before or played around with the language of it? All right. I'm happy to see that you're here after having looked at the language of it. That's a good sign. Yeah, so good that you're finding it attractive after playing with it a little bit. So let's see. So what I wanted to go over with you before we dive into the notebooks themselves on Julia Box are this idea of why do we want another language? Why is the language Julia getting developed in the first place? And then we'll talk about Julia in practice or an application of Julia, and then we'll dive into the tutorial itself. So this first question of why do we want a new language? And what I show here is this sort of periodic table of different programming languages color-coded by the features or the characteristics that those languages might bring to the table. And so the question is, with all of these existing languages out there, why is Julia getting designed? What niche does Julia fill? And the idea is that even with all of the existing languages out there, we still have something called the two-language problem. And for those of you that aren't familiar, this two-language problem comes from the classical divide that exists between the performance of a programming language and the productivity of a programming language. And so classically, there's this trade-off between what we think of as lower-level languages like C or Fortran that generate really efficient machine code, but take longer for us as programmers to get up and running in. And then on the other hand, we have these traditionally higher-level languages like Python or MATLAB that are easier for us to work in and to be productive in as programmers, but that don't generate machine code that runs as quickly. And so then traditionally we're forced between this trade-off between writing efficient code and writing code efficiently. And the trade-off though isn't really a true dichotomy, because the third variable to consider here is the generality of the programming language that we might use. And so, it is possible to generate fast or efficient code easily if we're working with domain-specific languages or, special libraries like NumPy, for example. But when we're working with those domain-specific languages or special libraries, the scope of the tools that we've chosen to work with will be limited. And so our real trade-off here is a trichotomy between performance, productivity, and generality when we're choosing a tool to program with. And so this is what gives us, the two-language problem, or the idea that we often have to start prototyping in one language to get something working and up and running rather quickly. And after we've got a working prototype, it's common for people to translate their code into a traditionally lower level language to get the speed that they might want to really have something running at scale. And so Julia was designed to address this two-language problem, where the tagline that we have for Julia is, looks like Python, feels like Lisp, and runs like C or Fortran. So the idea here is that Julia has been designed to offer you, a high-level language that gives you both, power and generality and ease of expression all at the same time. And so when I say that Julia offers productivity, generality, and performance, I'm gonna talk through what I mean when I say that Julia offers each of those features. And so we can start by talking about performance. So one of the things that we'll do in the tutorial today is a notebook that's called Julia is Fast. And so that's a benchmarking notebook where we'll look at a bunch of different implementations of the sum function. And so we'll look at some built-in versions of the sum function in Python and in Julia. But we'll also look at handwritten implementations of sum using the same algorithm in C, Julia, and Python. And so this sum function is just going to take a vector and then add together all the elements of that vector. And when we implement this in a handwritten way in C, we are going to see that to add together the elements of a 10 million element vector, it's going to take order of 10 milliseconds. When we do the same handwritten implementation in Python, we're going to be at order of 500 milliseconds. And then when we go to Julia from Python, we're going to be back down to order of 10 milliseconds. So the purpose of this benchmarking example is to give us a sense of, when you're writing something custom in Julia and just, sort of out of the box implementing something yourself, it gives you a sense of, how close Julia can get to C speeds. After talking about, performance, the next thing that I like to show is productivity. And one of the ways that we can sort of show off the productivity of Julia is by looking at how closely Julia code resembles Python. And so if we were to look at those two implementations of the sum function in Python and Julia side by side, what we see is that they're really not that different. So here, all of the differences between these two implementations are in bold. And so we see that there are a couple different required keywords, like in Python we have the def keyword and then a couple required colons, whereas in Julia we have the function and the end keyword. But other than that, we can express ourselves in pretty much the same way with a huge speed up in Julia. And it was this sort of difference, a difference in performance based on such small syntactic changes that got me really excited about starting to learn Julia as a Python user. And so I was using Python in my graduate research. And Sacha actually had come to Julia from a C and MATLAB background, so that was his incarnation of the two-language problem. And having come to Julia recently and been very excited about the language, he was raving about the language to me, and at some point he took a piece of code that I had written in Python and then translated it to Julia for me. And what I saw was that even though, on the surface he had only made a few, minor syntactic changes to my code, the code that he had written ran, more than an order of magnitude faster. And seeing that with such minor modifications I could get this huge speed up was really what got me excited about learning a new language. So the third thing that we say that Julia offers here is generality. And what I mean by that is that Julia is sufficiently general and powerful that that Julia is mostly able to be written in Julia itself. We also say that working in Julia feels like working in a Lisp. And what we mean by this is that Julia offers metaprogramming facilities like working with macros, and the design paradigm of Julia is multiple dispatch. Oh, I did mention this already, that most of Julia is written in Julia. And one of the things that's cool about this is that the fact that Julia is mostly written in Julia means that the line between users and developers of the language really starts to blur. And so a lot of our most important contributors to the language and generally to the package ecosystem are people who came to the language as users, often other graduate students. That's a very typical story. And what they find is that once they know the language well enough to write their own code in Julia, they know enough to also be able to look under the hood and start tweaking the performance of things or tweaking the functionality of the language to better suit their needs. And that's how they typically get progressively more entrenched in the language. And so the point there is that there's not a significant learning curve as there might be in other languages that are implemented in C under the hood. Okay, so what does actually working with Julia look like in practice? An application that I really like to talk about for Julia is the Celeste Project. And so the Celeste Project took data from the Sloan Digital Sky Survey, which was this effort to collect data on 35% of the visible sky. And so, in generating this data set, they came up with 178 terabytes of data, which I'm always forgetting what these prefixes mean. So tera, as a reminder, is 10 to the 14. So this is a data set of 1.78 times 10 to the 14 bytes. For a sense of scale, if you wanted to store all of this data on DVDs, it would take you over 25,000 DVDs to store that much data. If you wanted to be extremely silly and store this data on written paper, I did this conversion, sort of back of the envelope conversion, using some information I found online that said that we would take over 150,000 pickup trucks to store that amount of data on printed paper if we wanted to do that. So this is a relatively large data set. In the first 10 or so years that it was around, there wasn't a whole lot done with it. There wasn't a systematic approach, I guess, to going through all of this data set and trying to catalog the astronomical objects that had data collected on them in this survey. But what happened then was that a team of researchers came together to form the Celeste Research Project, and this brought together people with various backgrounds from, I think, MIT, UC Berkeley, Lawrence Berkeley National Lab, as well as Julia Computing, people that came in with statistics and physical science and also computer science backgrounds. And they decided to write software exclusively in Julia that would run on NERSC supercomputers. And so harnessing then both the power of Julia as their software and then these supercomputing machines as their hardware, what they were able to do was catalog 188 million stars and galaxies from this data set. And they were able to do this entire calculation in under 15 minutes. Now, in running this calculation, Julia actually became the third language to join the petaflop club after C and Fortran, so hitting over 1.5 petaflops per second. And this calculation made use of over 1 million threads and 9,000 nodes. So this gives us a scale or a sense of Julia's ability to parallelize or distribute on next generation machines. So this project in and of itself is impressive, but the natural question is what did Julia actually bring to the table here, and what would this project have looked like in the absence of Julia? And because we say that Julia has been designed to solve the two-language problem, maybe the first answer that you would come up with is like, well, if Julia hadn't been the language of choice, maybe 2 different languages would have been used in the project, and maybe there would have then been some sort of natural redundancy or inefficiency in needing to translate from one language to another. And while that's true, really the impact of using Julia on this project was more profound than that, because in bringing together a group of researchers with various different backgrounds, those again coming from the physical sciences and those coming from statistics and then computer science. The incarnation of the two-language problem in a diverse environment like that is typically that the team would have sort of fractured into one team of domain scientists, for example, who would have then done that first implementation or that first prototype of the software they needed in a higher level language, and then another sort of sub-team that would have taken that code when they were done and then done a translation to a lower level language. And so the way that the two-language problem would have looked in this environment probably would have been that one team would have finished their workflow before passing the baton off to the other sub-team. But instead, the fact that everybody was working in Julia from the beginning meant that everyone was working in the same code base, and that meant that the team was really able to function as a team and work more closely together and iterate more rapidly, so that really the science and the implementation of the science were able to sort of evolve together. And so with that, beyond academia, we're starting to see Julia uptake in various places in industry. Now that we're approaching the 1.0 release of the language very quickly, it's going to be released in August. We are seeing what's starting to look like exponential uptake of the language. And yeah, these statistics are from several months ago, but we're now well over 2 million downloads, and so we're hoping that your interest in the language will continue beyond this tutorial. And if you find yourself looking for additional resources to learn more about Julia after today, we have really active communities on Slack, Discourse, and GitHub, where there are lots of friendly people out there to answer your questions. I'm also providing my email here, and I have both business cards and Julia laptop stickers up here. So if you have any questions after today, if I can't answer them, I can probably direct you to somebody who can. So don't hesitate to reach out if you would like additional assistance. And so with that, we can dive into the tutorial itself. The link that I'm having you log in today is this one, so juliabox.com/up/AIPro/AIPro500K. Alternatively, if you are able to log in just at juliabox.com, but timeouts on juliabox.com happen after an hour and a half, and then you have to log back in. Whereas logging in here should give you a solid 4-hour session so that you can get through the tutorial without needing to log in multiple times. Are most people logged in already, or is there anyone that's not logged in yet?
Should we log in, or I have it on my machine already, so with that, do you recommend logging in?
There's no, if you have Jupyter notebooks and the tutorials all on your machine, then you're good to go. You don't have to log in here. But yeah, if you haven't done local installations of the language or the tutorials, then you can get all of that online. Okay. Yes. Mm-hmm. Yes. So you can use either GitHub, LinkedIn, or Google, I think, to log in. So whichever is most convenient for you. And I'll switch from presenter mode quickly. Let's see. Yeah, so these are your 3 options you were seeing to log in. Are those working all right for you? Mm-hmm. Oh, okay. Yeah, thank you. I hadn't encountered that before. You're good? Okay. All right, so once you've logged in then, there's this tutorials directory. And let me make this slightly larger. Are people in the back able to read at this font size? Yeah? Okay, great. All right, so there's this tutorials subdirectory. And then what we'll be working in today is this Intro to Julia tutorial. And so the first numbered, 13 notebooks, technically, are what I'll be doing sort of presenter style for you. And then we have a few exercises for you to work on your own to get more comfortable playing around with the language after we've gone through the presentation stuff. And for those of you that might have missed in the beginning, Sacha's primarily going to be addressing questions, so he's going to come around if you need any additional help. And then if there's a question that broadly benefits the audience, I'm happy to answer what I can as well. And so with that, we can get started then. So how many of you are familiar with Jupyter notebooks, having used them in Python? Okay, so a lot of you. Is there anyone, that seemed like everybody or almost everybody. Is there anyone that hasn't seen Jupyter notebooks before? Okay, cool. In that case, yeah, the purpose of this notebook is really just to show you how to work in a Jupyter notebook. So in this one, I'm just showing that you get whatever output is on the last line when you run a given cell, that you can suppress output with a semicolon. A couple things that are more specific to Julia here. If you precede any function that you're unfamiliar with in Julia with a question mark, either in a Jupyter notebook like this or at the REPL, then whatever doc strings are tied to that function will print to standard out. Also, if you were to precede any shell commands with a semicolon, again, either in Jupyter Notebook or at the REPL, you'll be able to work in sort of a shell mode. So here I'm listing all of the files in my current working directory and asking for the name of my current working directory here. So that was just to get us familiar with this environment. But since most of you have seen Jupyter Notebooks before, we can dive then into the first notebook, which is our first one that's more Julia specific. And also just to give you sort of a high level overview of the structure of the notebooks here. Really the first 6 notebooks on the language, notebooks 1 through 6, are meant to sort of give you a high-level tour of the syntax of the language. And then we start getting more into, I guess, Julia-specific features, talking a little bit about, for example, performance, the language design paradigm, and then also some special linear algebra functionality down in the later notebooks, here 9 through 12. And we have this sort of interlude with notebooks 7 and 8 where we talk about how to pull packages in into your environment and how to do some basic plotting. So we'll start with the sort of whirlwind tour of the language syntax, notebooks 1 through 6. And so notebook 1 here, getting started. Here I'll just show how to print in Julia, how to assign variables, how to comment, and then we'll look at syntax for basic math quickly. So first off, the most common way to print in Julia is to use this println function. And then for assigning variables in Julia, we don't need to, just as in Python, we don't need to specify the types of the variables when we declare them. So for example, we see that my answer 42 is an int 64, my pi is a float, and then here I've assigned a string to the smiley cat emoji. Once we've assigned a value to a variable, there's no issue with reassigning that variable, as in other dynamic or high-level languages, to another value of a different type. So smiley cat emoji used to be a string, now the smiley cat emoji is an integer. Programming with emojis is one good example of Julia being rather generic. So in Julia I could assign, for example, numbers or whatever values I might like to arbitrary emojis, and then I can create true statements like this one where we see that smiley cat emoji plus a frowny face turns us into a happy face. Yep. Yeah. So I'm really bad at this. What you're supposed to be able to do is hit backslash, and then, for example, if you type smiley cat and hit tab, but I'm really bad at holding the tab the appropriate amount. It seems like it only works for me like 50% of the time. What should happen is that you hit tab and then something comes, and then there should be a drop down that allows you to select the smiley face. Does that work for you? Yeah? Yeah, okay. I can never get it to work when I'm demoing in front of people. I think I exactly hit the character incorrectly, and then someone always explains to me how to do it, and they do it for me, and it works. But if it's working for you, then I guess the instructions are sound.
It helps if I type in part, if I type in
Uh-huh. Okay, that should work for me, but I'm glad that the instruction works. The instructions are sound, so if you do backslash and then, for example, smile or smiley cat, you can do emojis. I just can't do them because my fingers are broken. See, yeah, let me see. You would hit tab at this point?
Yeah, hit tab, that gives me a colon, and tab again.
Oh, okay. So it's 2 tab hits, really. Right. Okay. Thank you. Yeah. All right. So for commenting in Julia, we can comment with a single line, just using a hashtag or a pound sign. And if you want to do a multi-line comment, then you can do 2 hashtags and equal signs inside of those hashtags, and then you sandwich your comment between those. And then for basic math, the syntax will look pretty familiar, with the exception that to exponentiate things, we're using the caret symbol here rather than the double star that we would use in Python. And then at the end of every notebook, I have a couple sort of basic exercises to walk you through, where the idea is just that you start, executing code in Julia right away. And I ask for volunteers to answer the questions for me. So first off, if I wanted to look up documentation for the convert function, how would I look up docs for that in Julia? Yeah, question mark. So if I do question mark convert, we'll get our documentation. So what this is telling me is that to convert x to a value of type t, I'm passing the type that I want to get as the first input argument, and then the value that I want to convert as the second input argument. And so then here, our next exercise, we we say that we're starting with some variable called days. It's 365. I'm going to give myself some extra boxes. So this is an integer, but if I wanted to convert it to a float, how might I use convert to do that? What would I type? Yeah, I think what we should do here is specify float 64, and then we'll get that conversion. Thank you. And then this last exercise is just to play around with what happens when we try to convert, for example, a string that contains a 1 to an integer. And there we get an error, so that's not doing what we might want it to do. If you wanted to actually sort of pull a number out of a string, you can use the parse command. And one thing I'll point out, this will be relevant for one of the exercises later, and this is sort of starting to overlap with the next notebook, but if the 1 had been enclosed inside single quotation marks, then it would be a character rather than a string. And if I tried to do this conversion here, where I'm converting the 1 now inside the single quotation marks to an int, what I'm getting there is the ASCII representation. But we'll see more of that later. Any questions on the first notebook? Okay, cool. And we'll go to notebook 2. Oh, yes.
For your double function, the question marks, is there an equivalent of like double question marks in R, fuzzy matching, part of the function there?
Oh, no, but often if you try to look up docs for something that isn't the correct name, it'll make suggestions for you. So maybe that's relevant to your question or not. Yeah. Oh, okay. Oh, there's one way to find out. Okay. All right. Yeah. Cool. Yeah, thanks. Okay, so then we'll go to notebook 2 on strings. Okay, so the purpose of this notebook is to show you how to create a string in Julia, and then also how to interpolate and concatenate them. So first off, to get a string in Julia, the first way we might do that is to enclose some text inside a pair of double quotation marks. And the second way is to enclose text inside 3 sets of double quotation marks. One of the differences that we'll see between these 2 types of strings is that in the second type, we can add some additional formatting. So for example, if I add a bunch of basically new line characters here, Julia can tell that I wanted those new line characters or that formatting within this second type of string. So it just added a bunch of \n's here to my string. Also, in the first type of string, we're not able to quote inside the string itself because it's ambiguous, where the string actually ends. Whereas we don't have that ambiguity in the second type of string, so we're able to use quotation marks there around the word errors. And then what I started to show in the last notebook is that we can't create strings using single quotation marks in Julia. So single quotation marks around a character gives us a char type. And if we try to enclose multiple characters inside single quotation marks, we're going to get an error. So that's maybe one notable difference if you're coming from a Python background. And then for string interpolation in Julia, here we're starting off on creating a few variables, 1 for my name and then 2 for my numbers of digits. And to interpolate these variables or others inside a string, we would just throw a $sign within a string next to the variables of interest. So here I'm throwing the name variable inside this string, here are the num fingers and the num toes variables. And if I wanted to actually interpolate an expression within Julia, I could put a $sign next to parentheses enclosing the expression that I want to actually have evaluated within that string. So here we're adding 10 and 10 together before throwing the number 20 then inside the string. And then to concatenate strings, I'll show you 3 different ways to do that in Julia. Again, we'll start off here with some new variables. We've got this string S3 and the string S4, and we're bringing back the smiley cat emoji as the number 10. Here, if I use the string function, I can concatenate these two strings, S3 and S4 together to get the single string, how many cats is too many cats. And then I can respond with this second call to string. Here we see that I'm passing 3 input arguments to string rather than 2. So string actually takes arbitrary numbers of input arguments, and it will take not just other strings as inputs, but also whatever type you might like to pass. So here's smiley cat emoji, which is an int, is getting passed. And we get this single string output. I don't know, but 10 is too few. We could have created this first string a couple different ways. So we could have used the star operator to concatenate strings together. So when it looks like we're saying S3 times S4, we're really getting this single output string. We can't do string concatenation in Julia with the plus operator by default, though I'll show later in one of the exercises you'll see that you are able to define that method if you like it. And then the third way that we might do string concatenation is to just use string interpolation. So here I'm throwing $signs next to those strings S3 and S4 to get this single string output. Yeah?
Do string numbers come along with the quotation marks? Like, how would you only get the string without
You mean if I just wanted to display the text without?
Sure.
Yeah. I don't know. If you do println, does that? Yeah. Yeah, so I guess if you don't want to see the string character, or sorry, the quotation marks, then that'll work.
So the actual values come along with
No, yeah, those are just to denote for you that it is a string. Yeah. Okay, yeah. Other questions? Okay. All right. So this first exercise then, sort of the hint here, given that if we call the star operator, or sorry, rather, what I meant to say is, all right, if you were to exponentiate something in Julia, 2 to the 3, for example, what you're really doing is calling the star operator multiple times under the hood to do multiplication. And so given that piece of information, how might you create a string that says hi 1,000 times in Julia? Yeah, exactly. Yeah. Thank you. Let's see. Okay, so then this next one, I'm starting off with these two variables, a equals 3 and b equals 4. And what I want to do is create two different strings. The first string that I want to create is one that says 3 plus 4 using these variables a and b. How would I create that string?
Take one string and have the $sign plus $sign.
Yeah, exactly. Okay, and then how would I modify this if I wanted to actually get the number 7? Yep. If I throw in parentheses and get rid of that second $sign. Thank you. Any questions on this stuff so far? Cool. All right. Then we'll go to notebook 3, which is on data structures. So in this notebook, we'll cover how to create and work with tuples, dictionaries, and arrays in Julia. And for those of you that might not be familiar, sort of a high-level set of differences between these three data structures. Tuples are immutable, so once we've created a tuple, we can't update their contents, whereas dictionaries and arrays can be updated. Then both tuples and dictionaries are ordered collections of elements, whereas dictionaries are unordered and give us sort of associative relationships between two different sets of data. Okay, so with that, to create a tuple in Julia, we can throw our ordered collections of items or of elements inside parentheses. So that's just like in Python. So here I'm creating a tuple called My Favorite Animals. And one thing to note here is that Julia is 1 indexed. So we start counting from 1 rather than from 0. So the first element of my list here is the item penguins. And again, because tuples are immutable, we can't update them. So we will forever be stuck with penguins now as our first favorite animal rather than otters. Then to create a dictionary in Julia, we can use this dict keyword. And we could either initialize an empty dictionary just by saying dict and then with parentheses and nothing inside. Or if we want to initialize a dictionary to have key value pairs, we can use the syntax that I'm showing here, where we precede an arrow with the key that we want to add to our dictionary, and then follow that arrow with the value to be associated with that key. And the arrow that we have here is just an equal sign followed by a right-pointing arrowhead. And so here I'm creating this dictionary called My Phone Book that has 2 entries, one for Jenny and one for Ghostbusters. And now that we've created this dictionary, if we want to perform a lookup on the dictionary, we can just throw the key of interest inside square brackets after the dictionary name. So we can look up Jenny's phone number by throwing Jenny inside My Phone Book. And the syntax that we would use to add additional entries to this existing dictionary are very similar, where we're now throwing the new key inside square brackets and the new phone number to the right of an equal sign. And having done that, if we look at My Phone Book, we're now up to 3 input entries. If we wanted to remove an entry from a dictionary, we could use this pop bang command. And I'll explain in a later notebook why some functions end with a bang or an exclamation point. But for now, we'll just use pop bang, where the first input there is our dictionary, the second is the key from the key value pair that we want to remove. And then we see that we're back down to 2 entries now. And again, because dictionaries are not ordered, if I were to try to look for the first entry like this in My Phone Book, Julia thinks that I'm looking for a key called 1, and so returns a key error. Questions on this stuff so far? Yeah? Okay. And then to create arrays in Julia, we could enclose our ordered collections of elements inside square brackets. So here I have this array called My Friends. And one of the things that we see here when we get this output, so this is telling us that we have a 5-element array, and then the signature here is saying that this is a 1D array, or rather here it's a 1 for 1-dimensional, here array, and then the elements enclosed inside this 1D array then are strings. Similarly, if we were to look at the second array called Fibonacci, we're getting a similar sort of output where now we're seeing this is a 1D array that contains integers. Now if you want an array that has multiple types inside of it, that's perfectly fine. So mixture here has both numbers and strings inside of it, and what we're seeing here is that it's a 1D array that takes any as its input. So the type hierarchy in Julia, sort of you could imagine at the bottom of this tree we have concrete types like float64 and int64 and string, and then we have a few sort of abstract types on the next level, like number, for example, is going to encapsulate anything that's an integer or a floating point or the like. At the very top of our tree then is the any abstract type, where any concrete type will fall under that category. And so that's what Julia is defaulting to there. Now if we wanted to grab the third element of a list, we could do so with this syntax. So it's just like indexing into a tuple. If we wanted to edit an existing array, we could use this indexing sort of syntax and add our new value to the right of an equal sign here. And just like on dictionaries, we have the pop bang command to remove items from arrays, and now we have the push bang command to add items to existing arrays, where just like in Python, push is adding here the number 21 to the end of this array Fibonacci, and pop bang is always going to remove from the end of the array. We can check here that that's worked by looking inside Fibonacci. So all of these examples so far on arrays were on 1-dimensional arrays of scalar values. But we can also create arrays of other arrays, or generally arrays of other data structures. Or we can create multi-dimensional arrays. So And one thing I didn't mention so far, whenever we're working with a 1D array, like Fibonacci or mixture, for example, in Julia, one-dimensional arrays are aliased as vectors, so I could equivalently refer to this as a vector of integers, or a vector of type any here. And so moving into this next section there, one thing to note here is just vectors of vectors are distinct from matrices, for example. So a matrix is a 2D array, and yeah, multidimensional arrays generally are different from arrays of other data structures. And so here I'm creating a vector of vectors called favorites, and the signature that we're getting here can be read just like the ones we saw before, sort of from the outside in. So what this is telling us is that this is a 1D array where the types inside the 1D array are other 1D arrays that take strings. Similarly, numbers here is going to be a vector of integers. One command that allows us to create multidimensional arrays is this rand function. And so rand will take arbitrary numbers of input arguments, where integer input arguments to rand will specify the dimensions of the array that you want to create. So when I call rand on 4 and 3, I'm getting a 4x3 matrix, and the values inside that array are by default going to be floating point numbers between 0 and 1. Rand on 4, 3, and 2 is going to give us then a 3-dimensional array, or a 4x3x2 array. And then the last note to make about arrays before we move on to the next notebook is just to be careful when you're trying to copy arrays. So here, we've already seen this array called Fibonacci. If we wanted to copy Fibonacci and say that we tried to do that by saying some numbers equals Fibonacci, what we would see is that if we were to update this array called some numbers by, for example, indexing into it and then changing that first element to 404, we would see that if we were to then look inside Fibonacci, Fibonacci also is altered. And the reason is that when we did this assignment here, we weren't actually copying Fibonacci. We weren't actually creating a new array. We were just giving a second name to an existing data structure. And then it doesn't really matter which name we use to edit that data structure. So if we want to actually perform a copy, we're going to want to use the copy function. And so what I'm doing here is just restoring Fibonacci to its original state. Now if we properly copy Fibonacci using the copy function to get this new array called some more numbers, we see that we can update some more numbers here again at the first element, and then look inside Fibonacci and see that Fibonacci is unaltered. Okay, so we have a couple exercises here before we go on to the next notebook. So first off, we're going to start for 3.1 with this data structure called array. And then say that we want to add and then subsequently remove the number 4 to this array. So first adding 4 to array. How would we do that? Push, yeah. So push bang. Our first input then is going to be the name of the array, and then our second input is that number 4 that we want to tack onto the end. And now to remove that 4 from array. Pop bang, yeah. So this one only needs one input, so we're always taking from the end, so we return the 4 there, and if we wanted to check that that worked, we can add a new cell and look at array. Okay, so then in this next one, we already have this phone book called My Phone Book lying around. And let's say that we wanted to add this key value pair to it. So the key emergency and the phone number 911. Any ideas why this doesn't work based on either the error message or intuition? Yeah. Right, yeah. So what's happening here, if we look at my phone book, we see that this is a dictionary that has strings as both values and as keys. And this this type of dictionary was created at the moment that we initialized the dictionary. So if I scroll back up here to where we created my phone book, yeah, Julia looked at these first inputs that we gave to the dictionary when we created it and used that information to decide that this was going to be a dictionary that only took strings and strings. Alternatively, if we had initialized, for example, an empty dictionary, Julia wouldn't have any extra information to go on. So in that case, we're defaulting to creating a dictionary that has any type as both the key and the values. There will, of course, be cases where maybe you want to start by initializing a dictionary with a couple entries, but maybe you want your dictionary to be more flexible than would be indicated by just the initial entry that you're starting with, for example. In which case, like say, for example, I'm creating a dictionary that I know has this particular key value pair, but I want this to actually be an any type, an any dictionary. What I could do is that when I create this dictionary, I could annotate it to tell Julia that I explicitly want it to have a particular type. So I do that by using these curly brackets after the call to dict. And in this case, I'm both initializing with a particular key value pair and manually controlling the type of the data structure that gets created. And I think that sort of covers the last couple exercises. Let me see if I missed anything. Yeah, that was the purpose of these next couple exercises, just to show you that the way that you initialize a dictionary is going to create impact the type of data structure you get. Where here, for example, we're getting strings as the key type and any is the value type based on having different types passed as values for these two different entries. Any questions on any of the data structure stuff? Yeah. Uh-huh. Yeah. One way to do that would be if you can also create an array using the array function or constructor. So I think I'm actually going to look at the docs for this quickly. So to create an array, yeah, so the docs here are telling us how to specify the input type there, or rather the type that you want the data structure to have. So if I have an array of, I'm putting both the types that I want to occupy the array and then also the dimensionality. So this is creating a matrix. Or if I wanted a vector, we could do this. And we're just sort of randomly initializing the entries here, or taking, I don't know, does that randomly initialize or it just takes whatever's in memory? How does, yeah, okay. Yeah, so if you were creating an array in this way, for example, you could control the types. Oh, whatever's in memory, yeah. Yeah, if I had, for example, would I just do that like this? Yeah. Okay. Yeah, right. But I actually can't tell, is it creating a distinct object when I do this? Yeah, I guess I'd have to do something like this. I don't know if that actually gave me new information. Yeah. Under 07 is it copying? Sorry, under. Okay, all right. Yeah, so we're working right now on Julia 0.6. The most recent release is Julia 0.7, which is going to be functionally equivalent to Julia 1.0. The difference between 0.7 and 1.0 is that any changes that have been deprecated between 06 and 07 will generate warnings in 0.7, whereas you'll just get errors in 1.0. But otherwise, 0.7 and 1.0 will be equivalent. And so in 0.7, if you were to do something like this, you would then get copying of the array A to create B, whereas in 0.6, the version that we're working on right now, I'm getting the same object if I wrap array here sorry, the array A here in the array command to create B. So A and B here are the same. Right. Yeah.
Once out of slope to A after I initialized it, do I have to send like actual array of any or a number? How would I do it after A has already been initialized?
And sorry, you would want to update A to have the number?
Like 1.6. I want to like put 1.6 to A first.
Mm-hmm.
How would I do that? Probably it won't accept it. The float going to the array.
Right. Well, I guess I'm wondering if I did something like this. Oops, sorry. Should that? Yeah, it's not going to leave here. Right, okay. But I guess that error message there isn't particularly helpful. Yeah. Okay. Right. Mm-hmm. Oh, that's why you get that error. Okay. Yeah, so you would have to create a new data structure then. Okay. So with that, I guess we can go to notebook 4 then. So notebook 4 is on loop syntax in Julia. So in this I'll show the syntax for writing while and for loops. First off, the syntax for writing a while loop. We have just the while keyword and the end keyword, with typically our condition going on the same line as the while keyword, and then the loop body starting on the line in between the while and the end keywords. In Julia, we're for the most part whitespace insensitive, and so if I could write a while loop that counts from 1 to 10 like this. Alternatively, if I wanted to add arbitrary numbers of spaces, it's unambiguous what I'm trying to do here, since I have the end keyword, so I don't need to rely on indentation. I guess the way that we might say that Julia is not whitespace insensitive or is whitespace sensitive is that Julia is reading the new line characters here. So alternatively, I could put all of my loop body on one line if I added a semicolon to separate lines explicitly. Moving beyond the syntax for while loops, for loops are looking sort of similar, where now we've got the for keyword and the end keyword. We're taking whatever variable we want to loop over our loop iterable, using here an in keyword. And again, we're typically putting our loop body there between the for and the end keywords. So again, now we're counting from 1 to 10. One thing that I didn't show before is that, to get a range in Julia, we would use syntax like this, where we have a starting number and then an ending number for the end of our range separated by a colon. Alternatively, if we wanted to, take steps of different than 1 by default, we could add the step size explicitly between our starting and our end points of the array, and also add another colon there. Here we're looking at only the odd numbers. And similarly, using a for loop here just to iterate over all the entries of this array called my friends. In the next couple examples, I'm going to create addition tables with a couple different ways of writing nested for loops in Julia. And so when I say addition tables, what I mean is that I'll be generating matrices that have, as each entry in the matrix, the sum of the row and the column indices. And so we'll start by doing that by creating this matrix called A that starts off as a matrix of zeros. And we're creating A with this fill command here, where fill takes as the first input whatever we want to fill the subsequently created array with. As the second input to fill is a tuple that has as many entries as we want dimensions in our output array. So here, M and N are each 5, and so we're creating this 5 by 5 matrix. And then with this nested for loop here, we're iterating over all the entries of A and then updating them to, again, the sum of the column and the row indices. Now, with some syntactic sugar that we have in Julia, we could write exactly, this for loop, the nested for loop, using only a single for keyword and a single end keyword. And so we do that here. Again, we're initializing now a matrix B to be filled with zeros. And now we have that same nested for loop here, where what we've done is that we've brought, that second or the inner for loop onto the same line as the first for loop. So we have a comma now separating, whatever we're doing with I from whatever we're doing with J. And otherwise the loop body's looking the same. And the third way that we,
So it looks like Julia is one base in
yes, yeah. So we start counting from 1 in Julia. Oh, it's lazy, okay. Yeah. Sorry, could I... Yeah, with broadcasting. And yeah. Is broadcasting, I guess I only know the term broadcasting in the context of Julia, so is that a widely used term, or, yeah? In the party? Okay. Okay. Good to know. All right, and the third way that we could have created an addition table like this is by using an array comprehension, just like a list comprehension that you might see in Python, where now we're taking basically the condensed syntax from this nested for loop here, throwing it inside square brackets, like there, and then have our loop body effectively to the left of the for keyword. And so this is the first way that we've created an addition table where we didn't have to, pre-initialize a matrix of zeros to get things going. Yeah. Yeah, this is just syntactic. You'll get same performance for different ways of doing this under the hood. Okay. Okay. All right, so the first exercise, if I wanted to write a loop that goes over all integers between 1 and 100, and then we'll say it prints their squares, how would I write this? And it could be a while loop or for loop, as you will. Yeah, that'll get us an array of what we want, so that's great. Thank you. Yeah, and then the next one was just to do something similar but updating a dictionary. So the idea here was to create a dictionary called squares that here I'm just initializing as an empty dictionary. And then, for example, if I were to say for x in, again, 1 to 100, then on every iteration of the loop, I could add an entry to squares that is the square of the entry I'm adding, so something like that. And one thing that you'll notice if you're working in a Jupyter notebook, by default, if you execute some code of interest, for example, in a for loop, again, because Jupyter notebooks are not printing, they're only printing the last line, we would need to explicitly call, after running the for loop, the object to see what's inside it. And let's see. The last one here was just to do an array comprehension, which we already did, so I'll leave that up for a second. Any questions on the loop syntax that we just saw, or anything else? Yeah? You mean like in terms of performance differences or something like that? No, not to my knowledge. Yeah, no. Yeah. And I guess you just generally like a style guide for writing Julia code is what you're asking about. Yeah, we don't have anything super extensive. We have a couple recommendations, but yeah. Okay. So in the syntax whirlwind tour, we have 2 notebooks left, number 5 on conditionals and then 6 on functions. So going to notebook 5 on conditionals. First off, if you wanted to write just a sort of traditional conditional statement like this, we need the if, else, and end keywords. And then my first use of all of these keywords is my implementation of the FizzBuzz test. Who's heard of the FizzBuzz test? Is that a common? Okay, so some of you. So the idea of the FizzBuzz test is that it's a common question that you hear about on the internet that entry-level programmers will get when they're looking for a new job. The idea is that you're told you're given a number or a set of numbers, and you want to print fizz if each of the numbers in that set is divisible by 3, buzz if the numbers are divisible by 5, and then FizzBuzz if they're divisible by both 3 and 5. And so a couple new things we're seeing here. To say and in Julia, we use the ampersand. We're checking for equality with a double equal sign, and then otherwise doing the modulo operator with a percentage sign here. And so this is my then implementation of FizzBuzz, where with the number 42 we're printing fizz. One fun thing that I like to show in Julia is the use of ternary operators. So if we had in Julia a conditional statement like this, where we have if A, then B, else C, end, we could rewrite this statement just like this, with A question mark B colon C. And to give you an example of that then, if we say X is, let's see, X is 3, Y is 4. Here we have a conditional statement where we're just printing, or at least returning, whatever the larger of the 2 numbers is. And we could rewrite this statement just like so, where again, X greater than Y is the thing that we're checking to see if it's true or false. X is what we do or return if this statement is true, and then Y is what we return in the absence of X being true. So there we're, again, returning 4, the larger number. And one last thing that I like to show when we're talking about conditional evaluations in Julia is the use of short circuit evaluations. And so I told you that in Julia we use the ampersand to say and. Really, we could use either the ampersand or a double ampersand, where the difference is that by default, when we're using just a single ampersand in Julia, we're doing a sort of eager evaluation of this statement. So that's to say that Julia will look at A to see if A is true or false, and then independent of whether A is true or false, Julia is going to look at B to see if B is true or false. So for example, Julia might read the word false and then carry on to print high in this next clause. Alternatively, if we use a double ampersand to say and, then we're asking Julia to do short circuit evaluation. So in this case, Julia would exit this evaluation as soon as it sees false. So in that sense, we can use A ampersand ampersand B to conditionally evaluate B based on the veracity of A. So for example, if we say X greater than Y, ampersand ampersand print ln X, we just get to false and then we stop. And in this case, when we've reversed here, we actually get to the point where we print Y because Y is the larger number. Similarly, we can say or in Julia with a vertical line or a double vertical line, with the difference being that, if we're doing a sort of eager evaluation, we carry on to actually print high in the second clause even after we've already seen true, whereas if we short circuit, we end up just returning true and stopping there.
So how do you do
That's the single, the single vertical line would be bitwise or, yeah. Other questions on this stuff so far? We don't have case statements now. Oh, sorry, I guess I didn't understand. Yeah, in percent. What do you mean when you say array comparisons? I guess I'm not. Yeah, and we'll talk a little bit more about broadcasting in the next notebook. Okay. Let's see. Quickly through the exercises. Okay, so let's say that we want a conditional statement that prints a number if the number's even and prints the string odd if the number's odd. How might I do this? And then I'll ask you to do the same thing with the ternary operator. So we can just start with the regular if keywords for the first one. Any takers? Yeah, we can start with that. And I'll add some extra lines. So you were saying if what? Mm-hmm. Yep. 2 times equal sign? Oh, yeah. Sorry. Yep. Mm-hmm. Yeah, cool. Yeah. Thank you. And then if I wanted to do exactly this as a ternary operator, I'll bring this down so I can see both on the same screen. How might I rewrite that as a ternary? Yeah, so if I copy this clause, and then question mark, and then, what did you say? Mm-hmm. Yeah. So that's our ternary operator implementation. Yeah?
So for example, in Python, if we consider any non-zero value as true, like within context, but here I see that you have to answer it explicitly.
Yeah. One thing you could do, if you use the sort of bool constructor and wrap that around an integer, you could get that sort of interpretation. Where, yeah, similarly, bool 1 is giving us true. But yeah, by default, there is no, if I said if 0, this won't work if I tried to actually evaluate a number as a boolean.
Is there a concept of Python-minded? Is there a concept of a none type in Julia?
Is that null or null? Other questions so far? Okay. All right, so we'll go to notebook 6 then on functions. So in this notebook on functions, we're going to talk about how to declare a function in Julia, and then we'll talk about duck typing, then mutating versus non-mutating functions. So that's going to bring us back to how we saw earlier. There are some functions that end with a bang or an exclamation point, and others that don't. And finally, we'll talk about higher order functions, and it's in this last section 4 where we'll talk about broadcasting in Julia. And so first off, how to declare a function in Julia. I'll show you 3 different ways to do that, where the first way is to use the function and the end keywords. So what I'm doing here is I'm putting the name of the function I wish to declare on the same line as the function keyword. I'm throwing my input arguments to that function then inside parentheses after the function name. And then on the line between the function and the end keywords, I've got my function body. One thing that you'll see here is that I'm not explicitly saying return. So by default in Julia, whatever's on the last line of the function body is getting returned. If I wanted to, I could explicitly say I want to return the square of x here, for example. And that'll do exactly the same thing as if I just said x squared on the very last line. Then calling either of these functions, I would just throw the input arguments of interest in parentheses after the function names. And the second way that I could have declared functions exactly like this is without using the function or the end keywords. And I could do that by declaring a function like so, where now I have the function name, again followed by parentheses encapsulating my input arguments. And then to the right of the function name and input arguments, I have an equal sign. And then to the right of that, a function body. And I could call either of these functions now in exactly the same way that I called functions declared the first way. And the third way that I might have declared a function in Julia is using an anonymous function. Who's familiar with the concept of anonymous or lambda functions in Python? Some of you. Okay, so the reason that these are called anonymous functions is because we can actually declare a function that has no name, and subsequently, no way to access the function after having declared it. The syntax that we're using here to do that, or to create an anonymous function, is just putting the input arguments that will go to the function to the left of an arrow sign, where this arrow is just a dash followed by a right-pointing arrowhead. And then to the right of the arrowhead, we're putting the function body that makes use of whatever inputs are to the left here. Now, though this is an anonymous function, if I wanted to, I could bind a variable to a function like this, such that I can access the function thereafter. So if I say hi3 equals this, I've again declared this anonymous function, but now I have this variable called hi3 that I can use to access the function with the same syntax that I use to access or call functions that I've declared by the other means. Similarly here, I've got this variable called f3 that's bound to this sort of function map, or this map that's taking input x and squaring it, whatever x is. And I can call f3 the same way. Any questions on the syntax for declaring functions? Yeah? Yeah, you can. The only thing you need to do then is just enclose them in a tuple. Yeah, so that's how you would do that. Oops, oh, yeah, oh. I'll just show if I can do that. Other questions? Yes? Yeah, so the reason, I could have redefined f as a different function, but yeah, it's getting angry when or sorry, that's a little confusing. When I tried to define this function as f, what I was really trying to do here was create a variable called f that would be bound to this function. If alternatively, here I'll show you, if I had just said f is a function that prints this, now I've redefined the function f, but I'm not trying to change the type of f. Whereas if I had added an f here, f would be a variable rather than like a real function definition. And that's what's making Julia angry. It's that distinction, I guess. Is that at all clear? Or because if it's not, I imagine Sacha can word that much better than I'm able to. So the next section then is on duck typing in Julia. The idea that if it quacks like a duck, then it is a duck. What we mean here is that, or what we're starting to get at, is that Julia functions tend to work on whatever inputs make sense, or whenever there's an unambiguous way of calling a function, the function should just work. So for example, the say hi function that we defined above takes some input and then interpolates a string with that input. And previously we were calling say hi on other strings, but if we were to call say hi on an integer, string interpolation is defined to work on integers, and so it's unambiguous what we want say hi to do. Similarly, we have this function sitting around called f, which I redefined, and I don't want to do that, so bring f back to our squaring function. Okay, so we previously called f on integers. If instead we were to call f on a matrix, for example, this just works because it's unambiguous what we want. When we say that we want to square a matrix, we can just get the output of, or rather the matrix times itself. Similarly, we saw earlier in the tutorial when we were talking about strings that string interpolation is defined for the star operator, and that the star operator is called under the hood when we ask for exponentiation. So if I call my squaring function f on the string hi, I get this output string that's hi hi. On the other hand, if we were to call f, our squaring function, on a vector, or just a, oh, yeah.
Unimportant operations. So you said your three-dimensional array is a matrix.
Mm-hmm.
You can multiply matrices with an asterisk.
Mm-hmm.
The Python doesn't do that.
Oh, okay.
And another question I had is if you want to divide 1 divided by 2,
Mm-hmm.
are those integers or floats, or are you doing things like Python's way with slash and integer?
So yeah, by default you're going to get, if you do 1 divided by 2, you're going to get a float, 0.5, just like in, let's see. For integer arithmetic, I guess, do you mean, like, there are ways to get like floor and ceiling division, but I'm not sure.
So you do integer arithmetic and you want to do result. Well, standard Fortran, you do 1 divided by 2, you get 0. In Python, 2, you get 0, and 3, you get 1.5.
Yeah, so here what we're doing is, we have a 1D array or a vector here called v. If we try to call f on v, or try to square a vector, then we're getting this dimension mismatch, or this error message, where the reason is that it's unclear what we want if we're asking for a vector times a vector. It's not clear if we want like the inner product or the outer product, or if we want to do element-wise operations. And so Julia doesn't guess. Julia just tells us that it doesn't know how to deal with the ambiguity. Okay, so this section then on mutating versus non-mutating functions. So mutating functions are functions that will alter some of the inputs that have been passed to them, whereas non-mutating functions are creating a distinct output without actually altering the state of any of the inputs that you've given to that function. And by convention in Julia, mutating functions are followed by a bang or an exclamation point, whereas non-mutating functions don't have an exclamation point at the end by convention. So we can see the difference then between a mutating and a non-mutating function by looking at differences in behavior between sort and sort bang, for example. So if we do that here we have, again, a 1D array or a vector called v. And if we call sort on v, we are going to get this sorted output vector that starts with the number 2 now rather than the number 3. But after calling sort on v, if we look at v itself, v is still that original unsorted vector. Whereas if we instead called sort bang on v, we get the same output of 2, 3, 5. But if we look at v after calling sort bang, v itself is the sorted output vector. So we did an in-place sort there using the mutating version of sort. And then in this last section in this notebook, we can talk about higher order functions. So we can start by talking, oh, yeah.
Typically, for any function, a bang and nominate, or are those all different functions? Like, they're sort and sort bank, two separate functions?
Yeah, they're separate functions, but for most functions in Julia, there is a mutating and non-mutating function, or for many functions in Julia. Yeah. Right. Yeah. And yeah, thanks for the clarification. Other questions? Okay. I thought no hand. Okay. All right. All right. So in this section, we'll talk about mapping and broadcasting. So first off, mapping and broadcasting are both higher order functions, and what I mean when I say higher order functions are just functions that take other functions as their inputs. So with map being a classic example of this, map as the first input is typically taking map is taking a function as the first input, and then as the second and subsequent inputs, it'll take collections. And so what map does then is that it takes the function you've passed as that first input and applies it element-wise to the collections that are passed as those later inputs. So if I call map on F and then this vector holding the elements 1, 2, 3, I've just element-wise squared the entries of this vector. Higher order functions then are a great place to make use of anonymous or lambda functions that don't actually have variables bound to them. So recall that we could define, for example, a function that cubes things without giving it a name. And if we're passing a function as an input to a higher order function, then that input function doesn't actually need a name in order to be useful to us. So here we're telling map to do element-wise cubing on this vector with elements 1, 2, 3. Now for the purpose of this tutorial, I'm going to talk about the higher order function broadcast like it's basically a clone of map, though broadcast actually does exhibit, or it's able to handle more complicated situations than map. But for our purposes, we'll start with just calling broadcast the same way we called map. So here again doing element-wise squaring of the entries of this vector. One of the things that's cool about broadcast is that we have some special or syntactic sugar for calling broadcast without explicitly saying the word broadcast. So if we wanted to call broadcast on F and then this vector 1, 2, 3, instead of saying broadcast, we could just put a dot after the function that we wish to broadcast, then passing this collection as an input to F dot. So we'll see that behavior here. And just to sort of drive home the point in what we're doing when we're broadcasting and what this dot syntax does for us, if we had, for example, a matrix A, and we call F on A, then we're again getting matrix multiplication and returning the square of A. Whereas if we were to call F dot on A, then we're doing element-wise squaring of all the entries of that matrix. Where the idea there, one of the reasons that this dot syntax might be nice is that once we start writing more complicated mathematical expressions, it gives us a way to write something that looks a little bit maybe more natural or closer to the math that you would actually write down on paper. So here we have a dot associated with each operation to do broadcasting. Whereas we could have done this exact same thing, saying broadcast and then here generating a lambda or an anonymous function and passing the collection that we want to broadcast over. But I think, at least, there is some controversy over this, but for me and many other people I've talked to, it's a little bit more natural maybe to look at this first expression and see what's going on right away. Though there are some people that find this syntax more natural. I guess it's a personal preference. Okay. Yeah, so I didn't go over that. The difference is that map requires that, so if you were to map a function over multiple collections, so for example, you want to do element-wise addition of the entries in two matrices, for example, map is going to require that those collections that you're broadcasting your function over have the same dimensions. So there's a clear one-to-one mapping between, all of those entries. Broadcast doesn't require that the collections that you pass have the same dimensions. They have to share a common axis. But for example, if you could with broadcast add a matrix to a vector, and the common dimension, if you have a 3x3 matrix and a 3x1 vector, you could add that vector to each row of the matrix that is your first collection. Does that make sense, or yeah? Do you want to say that for maybe anyone that didn't follow me?
I guess the one question I have there is they have to have the same axis.
I guess it's like context based. Like whichever axis is shared is the one that it uses that information to generate an output where it's able to broadcast over the dimension that's shared.
I guess in your case, instead of a square matrix plus a 3x1, essentially it's like your second item is a vector, and you can technically apply 2 rows and 4 columns in a square matrix. So this is all
It's kind of the same. So you said you want 3x1, so it's not so kind of 3x4, 3x1, it's not 1.
Okay. So every vector is just a 3x1.
Yes, vectors are considered, broadcast vectors are considered embedded in the array fragmented array regardless of how many are necessary to have to broadcast the broadcast. Is that? Hence watching
So if you'll look at the exercises with me for a moment. So the first one, 6.1, is just declare a function that adds 1 to its input, and then we'll say it returns that the value of the input plus 1. How would we write this function in Julia? A few different ways to do it, so answerer's choice. Any takers?
The function says add 1, says, I guess, return. No, I'm sorry, you have to give it an input, so what was going to say?
I'll just call it X, I guess. Yeah. Oh, sorry, you wanted me to hit return. Mm-hmm.
X plus 1,
Mm-hmm.
1,
Yep. Thank you. All right, so if I wanted to explicitly use the word map or broadcast to, did I define an A yet? Yeah, okay, I've already got a matrix A. So let's say that I want to increment all of the entries of this matrix A, or rather return an object that has incremented all the entries of this matrix A using a call to either map or broadcast. And now this function add 1. How might I do that? Yeah.
You have to use that one.
No.
Map add 1A.
Yeah, you could do map add 1A. Thank you.
Also do map x 0, x plus 1, A.
Yeah, exactly. Thank you. So now if I wanted to do this exact same thing, one of these, using the broadcast dot syntax, how would I do that? Thank you. Any questions on any of the function stuff? Oh, a dot plus 1 like this? Oh, sorry, was that what you said initially, or? Oh, after you wanted this? Yeah, so that is a sort of strange inconsistency at first. So yeah, if we use the dot on any function that we've declared, like add 1, we're putting it after. But then with the plus sign, we're putting it before. You could alternatively, let's see. The dot does come after if you were to add like this, for example. But yeah, infix operators, is that the word that I'm looking for? Infix operators, Yes? Each element. Mm-hmm. Did that answer your question, or is there a follow-up? Or?
I know Python a NumPy array like a list of rows. Is it the same idea here?
No, so I guess we have a distinction then between like vectors of vectors, for example, and then matrices or higher dimensional arrays generally. So yeah, the elements of a matrix would be the entries of that matrix. Whereas, I mean, if you were, for example, to try to, if I did like add 1, if I had a vector of vectors, so something like this. If I tried to do that, it's going to, oh wait, that did work. Oh, I think this is an 06 thing, right? Sorry? Add 1 is defined here. But okay, so I think this is an 06 difference because, yeah. So on 07, if you were to do something like this, this would not work. So here we're sort of automatically broadcasting. On this version of Julia, this works because this works, where it's, yeah, inferring that we want the dot there in the older version. But yeah, in 07, if we were to run this command that's highlighted here, we would be trying to add vectors as the elements of this collection to integers and get an error. Okay. So with that, yeah.
So you have to broadcast if you want to do like element lines. Like I just tried like multiplying or adding, and it does like element lines, even if I don't use the dot on A. So like on later versions, you have to use dot connected.
Okay, so now we'll carry on with notebooks 7 through 12 before letting you work on some of these exercises on your own. First off, notebook 7, the purpose of this notebook is just to show you how to load in packages from the broader Julia ecosystem. At this point, Julia has about 1,700 registered packages, so we still have a relatively small ecosystem, but it's quickly growing. If you're interested in seeing all the packages that are out there, we have these websites, pkg.julialang.org, as well as juliaobserver.com, and those will show you all the packages that are out there and what they're for. But the purpose of this notebook is really just to show you how to use a package. And so if you worked on JuliaBox, whenever you work with a new package for the first time, you have to install it. And you would do that by calling the package manager, pkg, and then running pkg.add, where you put the name of the package that you want to install inside parentheses and inside quotation marks after this call to pkg.add. On JuliaBox, you won't need to do that, and so we can skip that line. But in general, whenever you're working on a local installation, you only have to run this once. It's just the first time for a given Julia installation that you're working with a new package. Then every time you're using a package in like a new REPL session or in a script or a new Jupyter notebook, you would need to use this using command to actually load the package. So here I'm saying using example to load the example package stored in example.jl here on GitHub. And if you were to actually go to this link, you would see the source code for the example package, where that just includes this definition for a function called hello that takes a string and then does a string interpolation here to greet whatever input you've passed. So now that I've used the example package, I have access to this function called hello, and I can call it here to print some Adele lyrics. Another example here of using a new package is this my use of the colors package. Again, we don't have to install colors today, but we can load the colors package with using colors. And now that we're using the colors package, I have access to this function called distinguishable colors, which here I'm telling it that I want 100 different distinguishable colors, and so I'm getting this output color palette. One sort of fun thing to do here is, we've seen this rand command a couple times to generate, arbitrarily dimensioned arrays. And by default, rand is populating the array that it creates with floating point numbers between 0 and 1. If we wanted to, we could pass a collection as the first input to rand, and then it will populate the array that it creates with elements from that collection. So here I'm creating an array that has integers between 1 and 10. Now that we have the colors palette, or what did I call it? I called it palette. The palette of colors. I could create a random matrix populated with different colors from palette. So this is sort of a fun one to run, because we are getting different colors every time. So if you do Project Euler at all, a very useful package for you to be familiar with is the primes package, here primes.jl. It'll allow you to do things very quickly with prime numbers. So given that the package I want is called primes, and it's located here, how would I actually start to get working with this package called primes? I can just say using primes, assuming I've already installed it. And now that I have this package, I have access to functions like a function called primes that allows me to get all of the prime numbers up until whatever input I've specified here. So I get to see that, for example, the largest prime number under 1 million is right there. It's 999,983. Any questions on loading or working with a new package? One thing that I didn't say here is that part of the design philosophy of Julia, or one thing that has been made a priority, is making sure that we can offer first-class function calls to other languages. So, for example, we have a package called PyCall that would allow you to use whatever functionality from Python you might want, and I guess more generally, you're able to load in not only built-in functions from Python and Python libraries, but also if you have code that you've written in Python and you wanted to start playing around with Julia without rewriting all your code at once, you would be able to import your Python code into a Julia environment and use it from within Julia. Okay. And if there aren't other questions on packages, we can then move to Notebook 8, which is our intro plotting notebook. I'm going to run the whole notebook at once. So what I'm going to be using to plot in this notebook is the plots package. There are a bunch of different ways to plot in Julia, including calling pyplot, for example. But one of the things that's nice about the plots package in particular is that it gives you a common set of syntax to work with a bunch of different backends, such that you could generate a plot with GR, for example, as your backend. Thereafter, you could change the syntax, thereafter you could change the backend that you want to use. So for example, maybe you want to move from using GR to using pyplot, but without actually changing any of the syntax that you used to, write the code that generated your plot in GR. You can just change the backend, keep the code, and get a different plot using plots. And so here we're loading the plots package. Here is some data that I'm going to be using that I data thieved off the internet as that we'll use to generate our first plot to get practicing with plots.jl. And so we have, for a few years between 1860 and 2000, global temperatures for those years, and then pirate populations corresponding to the same years that these temperatures are listed for. And we are going to plot one against the other to see if we can't find any underlying relationships between pirate populations and global temperatures. To get started, we will load our backend of choice, here GR. And once we have a backend loaded, we are now using this plot command and then scatter bang to create our first version of the plot, totally unannotated. One thing to note here is that I'm using scatter bang and then just regular plot. And the reason here that I'm doing that is that I'm calling the mutating version of scatter because I'm trying to mutate the plot that I create here to generate an overlay. If alternatively I just ran plot and then scatter, what I would get would actually be two separate plots. And you can play around with that if you're interested. But scatter bang is again creating this overlay between our scattered points and then our default line plot that we get with plot. We also will use now mutating commands to annotate the plot that we created in the cell above. So X label bang is creating our X label, Y label bang is labeling our Y axis, and then title bang is giving us that title at the top. And so now we get to start to see the influence of pirate populations on global warming with a fun little correlation versus causation joke. But one of the things that is a little unintuitive here, one of the things that makes this plot a little weird, is that the third variable that we have here besides global temperatures and pirate populations is time. And by default, Julia is plotting our number of pirates here on the lower axis, increasing from left to right. But actually pirate populations have dropped since 1860. So our third variable of time has it such that the way that things are plotted, it's kind of like we're looking backwards in time as we go from left to right. So if we want to look forward in time, we would want to just flip the x-axis. So here I'm using this xflip bang command to give us a view of temperatures versus pirate populations, which allows us to more clearly see that we need to reduce the number, or sorry, rather increase the number of pirates if we want to save the seals and whatnot. And now that we've generated that plot, we can use exactly the same code with a different backend just by calling here plotly.js, copy and paste the same code, and then get a very similar looking plot with the difference that plotly.js is going to give us more interactive plots. So now if I drag my mouse over the data, we can actually see what the values of those data points are. Yeah? Right, so that's just a Jupyter Notebook thing where it's just displaying whatever's on the last line. So if you were actually to label the plots that you created, so for example, like here if I said, P1, you could put them in different cells, or if you said like P1 is the plot and P2 is the scatter plot, then, I mean, thereafter I could display P1 like that. Yeah. Other questions so far? Okay. All right, so for exercises real fast. So I want to generate, let's see, I have a range here for x from -10 to 10. I'll add some extra cells. And then what if I want to plot a quadratic function over this range? How might I do that? I can show you two different ways. So the first way, if I were to first create an array called y, and what I'll do is I'll just square x here to generate that output. So here using broadcasting and exponentiation to get my y. So I could just say plot x and y to get the quadratic that way. Alternatively, without actually explicitly creating y, what I could do is I could say plot. I could pass the quadratic, or rather this squaring function, x to x squared, and then pass x as my input data, or my range on which to call this function, like so, and generate the same plot that way. So in this case, my first input is a function, and my second input is a range or an array. And in this other way of doing it, I had two input arrays, x and y. Okay. Let's see. I have an x now, so if I just execute this code, I'm showing here a way to generate a plot with subplots. So what we did was we created first these 4 plots, each with a different variable bound to them. And then we have this 5th call to plot where we pass all of the plots that we want to be used as subplots in that greater plot. So if I wanted to get, instead of a 2x2 grid of arrays, if I wanted to have a 4x1 grid, for example, how might I rewrite this or recode this? Yeah, exactly. It's this layout keyword. So yeah, the tuple that I'm passing to the layout keyword is specifying the dimensions of my subplot here. Other questions on plotting? Okay. So our next notebook then is the one that I talked about at the very beginning. Notebook 9, Julia is Fast, where we're going to talk about performance and do some benchmarking. So I'm going to run the whole thing at once again. So in this notebook, we are going to be looking at different implementations of, again, this sum function, where we're just adding together all the different elements of some vector called a passed to sum. And to get started with that, oh, and I guess maybe in particular what I should say is we're going to be looking at a handwritten implementation of sum in C, a handwritten in Julia, and a handwritten in Python. We'll also be looking at built-in versions of sum from NumPy, from Python itself, and then also a handwritten version, a built-in version from Julia. At the very end, this one we added recently, is a handwritten of Julia that's explicitly using SIMD. So, with that, we're starting here by declaring this vector called A, using that rand function, and we're asking for a vector that has, again, 10 million elements. And it's just sort of a sanity check that, you know, the sum function in Julia is working the way that we think it should. If we call sum on that vector A, we're getting an output that's equal to about 5 million. So we've got, you know, about 10 million times roughly 0.5 as the average element in this array. So that's, you know, seems to be working. We have a couple different ways to, you know, benchmark functions in Julia. By default, just in the base language, we could use this @time macro to see how long it takes to run, you know, sum called on A. But we will see that just using, you know, this built-in macro @time, we're going to get a lot of variation from one call to another. And so one way to get more consistent results, or you know, have a better idea of how long it actually takes for a given operation to execute, we can use this package called benchmark tools. So benchmark tools is going to give us macros like, we'll see this later, but add benchmark, for example, which will give us sort of a printout of statistics from multiple runs on a given piece of code. So it'll tell us, you know, I ran this piece of code 100 times, and the fastest time it ever was this, and the slowest time was that. And so we can get a better sense of, you know, what's going on and how long something might take. So now that we're using benchmark tools, we can start by looking at the handwritten version of sum in C. And I didn't create the original version of this notebook, so I don't know much C. But the important point here is that, you know, we can actually write C within our Julia environment. So we can, you know, for example, declare some function called C, called sum from within C, and then subsequently compile from, again, within, you know, our Jupyter notebook, or generally within a Julia environment. And then at the end of the day, we have this function here called csum that will, you know, call C code under the hood whenever this function is run. So if we call csum now on this vector A, we're again getting about 5 million. To be a little bit more precise and make sure that csum is working the same way that the built-in sum in Julia is working, we can use this isApproximate function to check that within maybe floating point error by default or so, the output of these two things are equivalent. And we see that csum and sum are behaving similarly. Another sanity check there. And that once we've done that, we can then actually benchmark csum with this @benchmark macro. What we're seeing here is that in the best case scenario for this 10 million element array, it's taking about 12 milliseconds to add together all the elements of this vector. So what we're going to do to just keep track of how all the different implementations do here, we're going to take that minimum time from our benchmarking output and then add it to this dictionary called D so that we can see how, at once how everything is doing. And so if we then move to Python's built-in sum, we can grab the built-in version of sum from Python using the pycall package. So the pycall package that we're using here is providing us with this functionality array to py and then the py built-in function. Py built-in is allowing us to specify the function from Python that we want, and then within our current scope we're renaming Python sum as PySum. Once we have PySum, we do the same sort of sanity checks to make sure that PySum is performing the same way that sum is. So it's the function that we want. And then we can benchmark PySum and again grab the best case scenario or the best time, which here was about 156 milliseconds. So once we've done that, we can then look at the built-in version of sum from Python's NumPy. So to grab functions from NumPy, here we're using the conda package, and then importing the function that we want from NumPy. Here we're calling this NumPy sum within our current scope, and then we're benchmarking NumPy sum here. And we see that the minimum runtime for NumPy sum is only about 7 milliseconds, and we're adding that then to our output dictionary D. So one thing to point out at this point is that NumPy is doing a lot better than C, but the reason is just that the C code that we have here is just the fastest or the easiest thing that we could write up to write our own implementation of sum. So there's no optimization here for the C, whereas Python's NumPy is obviously going to have a lot more optimization under the hood from people that know what they're doing. So before moving to Julia, we can then look at the handwritten version of sum in Python. So this one we're calling py_sum, or sorry, well here we're calling it PySum, and then it's kind of confusing. We rename it in our current scope to SumPy. So we're declaring here using this py, py, and then the triple quotes to tell Julia that we're writing Python code here. And then we're benchmarking SumPy and seeing that our best case scenario with our handwritten version of Python is giving us about 464 milliseconds. Okay, so when we look at Julia's built-in version of sum, one of the first things to note is that Julia's built-in version of sum is actually just written in Julia. It's not implemented in another language under the hood. And you could see that if you were to go to this reduce.jl file, line 359 is where the sum function in Julia is defined. When we benchmark sum in Julia using the benchmark version, we're around 7 milliseconds as our best runtime. And so we'll add that to our output dictionary. And then here, if we write our own version of sum, again looking pretty similar to the code that we used to implement sum in Python, handwritten, and then benchmark our version, we're a little under 13 milliseconds now for Julia. And this final example in Julia, I'll talk about all the results one by one at the end, but this final result, we're explicitly using SIMD, or single instruction multiple dispatch, or multiple data, using this @SIMD macro. And we're seeing that we're, again, at about 7 milliseconds when we explicitly call @SIMD. Is there a question? Or, no? Okay, so when we look at the output of all of these in this summary at the end, there are a couple takeaways. One of the takeaways is that if we look at the handwritten version of sum in Julia and C side by side, they're performing pretty comparably. Julia is approaching C speeds there. Another thing to note is that Julia's built-in is taking about as much time as Python NumPy's built-in. Again, so yeah, benchmark tools is giving us a better way of benchmarking than just using the out-of-the-box at time macro, but there still will be some variation from time to time. So Julia's, basically the difference that we're seeing between Julia's built-in and Python's NumPy's built-in, this like 0.3 millisecond difference there, that's really not meaningful. From one run to another, like sometimes NumPy is beating Julia and sometimes Julia is beating NumPy. So they're really neck and neck. But beyond the fact that, Julia's built-in, for example, which again is written in Julia itself, beyond the fact that that's, really fast and the fact that, Julia's handwritten is doing pretty well, one of the things that's cool here is that, we're getting most of the performance that we might want when we just write the easiest version of sum or implement sum in the most basic way out of the box that we could. We have like roughly a factor of 2 difference here between the Julia handwritten and the Julia built-in, but like that factor of 2 differences in this case amounting to a handful of milliseconds. So that's another one of the takeaways. Also, one of my colleagues added this SIMD example recently, and I'm not totally sure what the takeaway from the SIMD example is supposed to be. I'm not sure if you have greater insight there. I don't know if the point is that you don't get a specific or a performance boost, and therefore the point is merely that like you do really well without explicitly asking for SIMD. Or I guess you got a performance boost relative to your handwritten. So I guess just using the @SIMD macro, you basically got to the performance that the built-in version has. So I guess that's the takeaway. Right. Okay. Okay. Any questions on this one? Okay. All right, so the next notebook then is on the design paradigm or multiple dispatch. So trying to answer the question, why is Julia fast? Now that we've talked a little bit about performance. Who has heard of multiple dispatch? Is that a little bit, some of you? One thing that helped me a lot with starting to understand multiple dispatch was thinking about multiple dispatch in sort of the context of object-oriented programming. So before I go through the notebook on multiple dispatch, who's familiar with the concept of object-oriented programming? Most people? Okay, cool. So in object-oriented programming is making use of single dispatch, where the idea, I guess what we should say is, in object-oriented programming, the method that you use when you make a function call is determined by, some privileged class of objects. So for example, if, for example, I defined 2 different classes, one called cat and one called dog, and I defined some say hi method for each of those classes. Say that, for example, when I call say hi on a cat instance of, an instance of the cat class, I'm going to get a meow. Whereas if I call say hi on some object created from the dog class, I'm going to get a bark. So then what's happening, when I'm calling say hi and then subsequently getting either a meow or a bark, is that effectively the type of the object, its status as being either a cat or a dog, is determining at the end of the day what version of the function say hi is actually being dispatched. So I've sort of given this privileged status then to one of the input arguments to the function say hi, where when I call say hi on a cat or a dog, often the syntax is a little bit different. from the other inputs that get passed to the function say hi. Like maybe I have, Fido is my dog, and I'm saying Fido dot say hi. But fundamentally, Fido is still an input to the function say hi, and Fido's status as a dog is what's ultimately determining what happens. So this is an instance of single dispatch in the sense that this one input is determining what happens. In multiple dispatch, all of the input arguments to a given function and the types of all of those inputs will determine ultimately which method associated with that function is getting dispatched. So there's no privileged input argument like the class of an object that would determine what method you get at the end of the day. And so we'll walk through some examples of multiple dispatch in this notebook, hopefully to clarify what's going on with multiple dispatch a bit more. And I'd like to start by talking about things we've already seen. So we've already seen that we could declare a function called f, for example, that squares its input, and without giving any information to Julia about what inputs we want f to take, Julia can figure out that it's able to square numbers and matrices and strings, but not vectors. And if we wanted to, though, we could actually specify the types of input arguments that get fed to a given function. So, for example, if I were to declare a function called foo, I could say, all right, foo is going to take two inputs, x and y, and I can restrict the types that are acceptable for x and y to both be strings. And I'm doing that here just by saying : string after the input x and : string after the input y. And when I call foo now on two string inputs, I want this printout to come to standard out, which is going to say my input x and y are both strings. So once I've declared foo in this way, I could call foo on the inputs hello and hi, get this expected printout, and if I were to call foo on 3 and 4, I'm going to get a method error because I didn't define foo in a way that allows it to accept integers, 3 and 4. Now if I wanted foo to be able to work here, if I wanted this call to work, then I might define foo in a way where foo will take integers. So now I'm specifying that x and y each have to be of type int. And in this case, now if I call foo on two integers, I want the printout to tell me that both x and y are integers. So I'm declaring foo this way. Now if I call foo on 3 and 4, I'm getting that x and y are both integers in my printout. But the thing is that if I go back and I call foo on the inputs hello and hi, I'm still getting this printout that x and y are both strings. And so what's happening here, or the idea that I'm trying to convey, is that when we declared foo to take two integers up here, we didn't actually overwrite the definition of foo. We didn't redefine foo to be to replace the first definition of foo that we had. What we've done is we've added a second definition to foo, and we can see that here. When we declared foo this second time, we're seeing that foo is a generic function that has two methods. So we can have many different methods sitting around tied to a particular function. So at sort of the heart of multiple dispatch is this distinction between then methods and generic functions, where generic functions are sort of, we can think of generic functions as like the abstract ideas that get tied to particular operations. So we have in our minds, for example, the idea of what it means to add two things together. And we typically associate addition with the plus operator. But on a computer, if you actually want to add two things together, then you need particular implementations for, like, how do I add together two float 64s, or how do I add together two int 64s? And so, in Julia, making use of multiple dispatch, we can have many different methods or many specific implementations tied to one function name, and then the compiler is going to dispatch the appropriate method, or the appropriate method for the input types that we've passed to just a generic function call. So we then, as the users, don't have to think so much about which implementation we need, but we're still able to get the benefits of working with methods that are written for very specific or for concrete types. And to give you a sense of what methods might be tied to a generic function, we have this methods function. So if we call methods on foo, we see that there are two methods, there are two different definitions for foo lying around, the two that we declared. If we were to look at methods on the plus operator, we see that there are 100 and, oh, yep.
Sorry, just a general question about I guess. I was thinking that one implementation might be saying, like, to add wrong items or wrong number of variable inputs or something. So, like, in the example,
I guess in terms of like best practices, I mean, you could always add like assert statements if you want to like check if something is true. I guess I'm not totally sure how to field that question because yeah, do you have a good answer about best practices for using multiple dispatch in that context?
Sure. You can do that, yes. Say that you always write the second method, because if an method is like this, or the wrong method type, or go to compare anyway. So that's all the advice. However, if you want to throw a compare method on the calculation, then you would certainly could write one method for and says I use one of sort of thing, or I use it in another sort of formula. Is that I guess more
Yeah.
what was the last step?
I'll just want to do that.
Okay, so yeah, if we call methods on plus, we see that there are 180 different ways to add things together in Julia. So this is basically like a combinatorics problem of sorts, where we can see that we have different methods for adding together big floats and unions, or dates, or what have you. Any two types that we might want to add together, there's probably a way already implemented to do that. Another command that we have here is the @which macro. So if we call @which on foo 3.4, what @which returns for us is information about which version or which method actually got dispatched when we called foo on this particular set of input types. So here we see that when we call foo on 3 and 4, the version of foo that's going to get used is the version that's written for in64s. Similarly, if we called @which on 3.0 and 3.0, we would see that the version of addition that's going to get used is the one that's written for float 64s. Now moving beyond writing methods for concrete types in Julia, we can also write methods for abstract types. So for example, if we were to say, foo takes now two numbers, x and y, we could write a definition like this. And now, even though we haven't actually implemented something specifically for floats, if we were to call foo on two floating point numbers, we're going to get the version of foo that is written for numbers. But note that Julia is always going to default to using the version or the method associated with the generic function that's implemented for the most specific use cases that you've already written something for. So if I call foo on 3 and 4, we go back to using the integer version rather than the numbers version of foo. And at the end of the day, we always can implement a more generic or like a fallback method. Like here, where we're saying foo of x and y, where this would be equivalent to explicitly saying, for example, that we will allow x to be of type any. And in this case, we're going to do this printout that says, I accept inputs of any type. And now if I were to call foo on two vector inputs, I'm getting that really generic method. And so if I wanted to write, oh, yep. Yeah, it includes complex numbers. Yeah. Yeah. Other questions? No? Okay. All right, so let's extend the functionality of foo. So let's say I want to write a definition of foo that is going to print foo with one Boolean. Okay, what would my input arguments look like for this? And let's see, I said in the prompt that it only needs one input argument type. It's going to be, say again? Yeah, x : bool. And then we can check that that works just by running foo on the input true. So for the notebooks that I'll be running you through, I've got 2 quick ones on linear algebra, and then you can get to doing exercises on your own. So the first one on linear algebra is just more basic syntax for linear algebra. So this is notebook 11. And we'll start this notebook by creating a matrix A with the rand function and then a vector x with the fill function. First thing we see is that matrix vector multiplication is defined with the star operator in Julia. So we can say B equals A star x. If we want to transpose a matrix, we can get the conjugate transpose just by adding an apostrophe after a matrix. If we don't want conjugation and we simply want a transpose, then we can call transpose on A. And if you want to do multiplication of a transpose object and another object, you don't explicitly need the star operator. So if you wanted to do the transpose of A times A, or rather the conjugate transpose of A times A, you could just say A prime A, and that's sufficiently unambiguous that Julia knows you're trying to multiply these objects together. If you want to solve a linear system in Julia, you can use the backslash operator. So I can say A backslash B. This will work, independent of the dimensions of the matrix A. So if I, for example, have a tall matrix A, or one that's represents an overdetermined system, I could say A tall backslash B, and now I'm just going to get the least squares solution. Similarly, if I had, for example, a rank deficient matrix. So here I'm creating this matrix called rank def. What I'm doing is that I'm creating a vector V here, and then I use that same vector to generate the columns of the matrix rank def. So now if I were to try to solve this linear system, I'm just going to get whatever the minimum norm least squares solution is. And finally, if I wanted to work with an underdetermined system, or a sort of short and wide matrix, A short, again, I would get the minimum norm solution if I do A short backslash B short here. All right. So from what we saw in this notebook, if we wanted, I already have a vector V. If I wanted to get the outer product of vector V with itself, how might I do that? Yeah. In this case, if I do explicitly need the star there, I sort of need the, if I reverse the order of these to get the inner product, then I could just do V prime V. But here I would get confused and think that I have an object VV. So, yeah. So yeah, there's my outer product and my inner product of V with itself. Any questions on this notebook? Okay. So our last notebook then is notebook 12, which is factorizations and other fun. And so in this, I'm going to go over syntax for doing a couple different factorizations in Julia. Then we'll talk a little bit about special matrix structure and generic linear algebra. So first off, we're setting up a linear system to get started. B equals A times X. And what we'll see in Julia is that the naming scheme for factorizations is pretty consistent. So for example, we're going to encounter functions like LU fact to give you an LU factorization, QR fact to give you a QR factorization. There's also IG fact, HES fact, SVD fact. And what happens is that when you use a function like LU fact, for example, to do an LU factorization, is that you'll return a factorization object. So in the case of an LU factorization, you've got this base.linelg.lu object that comes out. Here I'm naming it ALU. And we'll see that that's the type if we call type of on ALU. If you want to grab the individual matrices that you should have gotten out of that factorization, you can get those matrices by indexing into this factorization object with symbols. So symbols in Julia are created with a colon and then a character or a set of characters. So this is the symbol P, the symbol L, the symbol U. If I index into this factorization object ALU with the symbol P, I'm grabbing my permutation matrix. ALU, grabbing the lower triangular matrix, I can do with this symbol L, and I get the upper We can then, I've shown already that we can solve linear systems with the backslash. We also have methods to solve linear systems using not just the original matrix A, but also the factorization object that we would have gotten out of ALU, for example. And similarly, we have methods like det, which will give us the determinant of a matrix A, will also give us the same output if we were to call det on the factorization object from A, or from factorizing A, rather. We would see very similar things if we use QR fact, for example, to do a QR factorization. Though in this case, the symbols that we need to index into this factorization object and grab the matrices from that factorization will be different. So in the case of a QR factorization, we have the Q symbol to grab our orthogonal matrix and the R symbol. And for an SVD, an eigendecomposition here, using IFACT, we could use these values and vectors symbols in order to grab our eigenvalues and our eigenvectors. Another thing to note here, actually run all of these lines, when we calculate the inverse of the factorization object asim eig that got created up here, if we ask for the inverse of this object, the way that the inverse is actually being calculated in this case is that we're going to use the eigenvectors and the eigenvalues, like so, under the hood to calculate that inverse. And so the next section in this notebook then is on special matrix structures. The point of this section of the notebook is to show you how in Julia you can take advantage of underlying patterns in the structure of your matrix. So for example, we're starting here by initializing a 1,000 by 1,000 matrix, and then we're using that matrix and its transpose to construct some symmetric matrix called asim. Now right away, if we ask Julia, is this matrix asim symmetric with the function is symmetric, Julia says true. So Julia can tell that this is a symmetric matrix. Now the reality, of course, is that when you're doing linear algebra numerically, we're going to accumulate floating point error over the course of doing operations. And so I'm going to simulate the accumulation of floating point error here by just adding a little bit of noise to one of the entries of a symmetric matrix. So here, we're creating a matrix called asim noisy, which is initially just a direct copy of asim. And then we index into just one of the entries of asim noisy. We add 5 Fs, and to show you how big 5 Fs is, it's a little bit bigger than floating point error, so order of 10 to the negative 15. And so already, now that we have asim noisy, if we ask Julia, is asim noisy a symmetric matrix, Julia has to say no, because Julia can't tell if this amount of noise is intentionally there or accidentally, and so it can't assume that it can just ignore that difference in one of the values. But if we wanted to, we could explicitly tell Julia that asim noisy is a symmetric matrix, and we could do that using this symmetric function. Similarly, we have functions like sim tridiagonal, tridiagonal, diagonal, triangular, all these different functions to tell Julia explicitly about the structure of a matrix that we might be working with. And so here I'm creating this new matrix called asim explicit that I'm telling Julia is a symmetric matrix. So saying we can ignore the floating point error. And what we're doing here then is running the same operation where we're grabbing the eigenvalues of a given matrix on each of these 3 matrices that we've just created. On asim, asim noisy, and asim explicit. So the point is to see performance differences in working with a noisy matrix or one that Julia can't infer the structure of versus those that either Julia can tell by itself or has been told explicitly are structured. So what we're seeing is that it's taking almost an order of magnitude longer when we aren't able to take advantage of the special structure of a matrix to do the same operation. A similar sort of example here. I get this question a lot. So just to note, you can add underscores to numbers like this without functionally changing anything. So this is just for readability that the number 1,000,000 has these 2 underscores. So what we're doing here is that we're creating a matrix A that's going to be symmetric tridiagonal. That's 1,000,000 by 1,000,000. So it's going to have 10 to the 12 different entries in the dense matrix. But that dense matrix would only have 3 bands in the center that were actually non-zero. And what we're doing here then is timing how long it takes to get the maximum eigenvalue of this million by million matrix. And it takes just a little over a second. So if we actually had to work with the full dense matrix and weren't able to take advantage of this matrix structure, we wouldn't be able to run a calculation like this on a laptop. And the final section here is on generic linear algebra. So one of the things I haven't shown yet is that rational numbers are built in Julia. So if I say 1//2, I get the number 1/2 rather than 0.5. And the traditional way of providing support for linear algebra in a new language is just to wrap BLAS and LAPACK routines, which is still what's done in Julia for certain types, like float 32, float 64, and then complex numbers built from both of those types. But Julia now goes a step beyond that and offers support for generic linear algebra such that we could build, linear systems that are composed of rational numbers, for example. And then we could continue to work with rational numbers as we work with that linear system. So here, we're creating a matrix called A rational that stores all rational numbers. And what we're seeing here is that we could do matrix vector multiplication or solve a linear system or do an LU factorization and return output objects that have all rational numbers rather than promoting to floating point numbers or getting division. Any questions on this stuff? Okay, I have one last set of exercises where I give you exercises to work on your own. So the first one, so we'll declare this matrix called A, which I'll do by just copying this bit. And then I'll add some extra cells. All right, so let's say that I want to grab the eigenvalues of this matrix called A. How might I do that? I think we have a couple different ways. We could say eigenvals on A, for example, or if we had first done like an eigen decomposition on A, we could then index into the object that we're going to get out of that and use the values symbol to grab those eigenvalues. And then, okay, so this next one, create a diagonal matrix from the eigenvalues of A. One of the things that we should see here is that, if I were to just wrap the matrix A in this diagonal command, it's going to just grab whatever the matrix, or sorry, whatever the diagonal of the matrix A was, and then create this new special matrix, or sorry, structure, or matrix with special structure that uses that diagonal. Okay, so what if I wanted to create a lower triagonal matrix from A? In that case, I can just use this keyword and wrap it around. And then we grab the lower triangular part. So with that, you're definitely free to ask more questions. But my plan for the next part of this is just to have you work through some of the exercises that we have here. So the first one that I have is just to calculate pi using a Monte Carlo simulation. So that's explained in here. And I really like this exercise because it requires that you use a couple different programming constructs, and the purpose of the exercise is just to get you practicing using Julia's syntax. So yeah, you'll basically use a random number generator to pick a bunch of points falling within a square, and then figure out how often those points that you've picked within the square fall also inside a circle that has a radius equal to half the length of the square. And once you've done that, you can calculate pi because, yeah, based on the probability that a point falls in both the circle and the square. So this is our formula for pi then. So you can try that one out. And then I also have, so there are 4 exercises in total in this directory. They are calculate pi, compressing an image. So this is image compression with an SVD. And then we have create a Caesar cipher. and then this exploring benchmarking and performance, which is going to talk a little bit about type stability. So those are the 4 exercises. We have solutions. I'm also happy to go over solutions. So I think what I'm going to do is on our Slack channel, I'm going to put out 4 pings that say I've finished this exercise, I've finished this exercise, and whatnot. And as you finish exercises, if you could just like thumbs up the ones that you've done, and then maybe when most people have finished a given exercise, we can look at the solution together or so.